So the subject of today's lecture is, as I mentioned on Tuesday, is kind of trying to straddle the common ground between what Piers Coleman told you, introducing superconductivity, and what Jean-Noël Fuchs told you about the topological aspects of it. So topological superconductivity is my attempt to trying to combine these two. Now, I won't hide from you the fact that it's a rather rich subject, and so invariably I will have to drop certain things. And once at the end of the lecture, I'll tell you what it is that I've dropped, okay? But I'll start, hopefully gently, and then we'll see how far we can get in this. So I kind of outlined the plan over here, and I'll follow the example of Giovanni, and I will try to put tick marks once I go through. So let me first say, just in a few words, that the actual subject of topological superconductivity did not start, let's say, 10 years ago. Not even 15 years ago. It actually goes back much longer, or much earlier, to 1970s. However, it is fair to say that the words topological superconductor have entered the condensed matter physics sort of more broadly and now are much more recognized after the work around 2008, 2009 by a gang of four who've done the so-called tenfold wave classification, as well as Alexei Kitaev. And I'll remark more of the history as I go along, but this is just to tell you that at least the first part of the lecture isn't something that's very, very new. It's actually been known for a good part of 40 years, okay? Now, the first part I would have to do is to tell you a little bit about a formalism that I'm going to use. So Giovanni as well as Piers have introduced the field operators, right? Now, when we think of a superconductor, right, one way to think about this is that I'm going to use the psi to denote the field operator. And this, you should think of this as a number, right, particle number. And so in the form in a Hamiltonian, this is actually something similar to what Giovanni wrote down here, earlier today. You could generally write down a form like this. So this is in a so-called first quantized notation, whether this is field operators or sometimes people write this in a second quantized notation. But that would be a kinetic energy term. So when I write down what I mean by this epsilon k, it's h bar squared, k squared over 2m. That's the energy that enters here if it was just a simple parabolic band. Or if you start from a tight binding model, then generally this would be a Fourier transform of some hopping matrix, right? So for instance, if I were to do Fourier transform of this, alternatively, I could write this down in the way Giovanni wrote earlier today and write this down as a sum over ij, tij, and write this down as ci dag as cj, where these operators are defined in the Vanier basis that Giovanni introduced this morning. Okay, so this is just to let you know that this is one-to-one correspondence. Now, when we talk about superconductivity, as Piers remarked, we haven't yet covered the BCS theory, but at the level of the Hamiltonian, the way you could think about the pairing is that, remember, the two electrons have to get together to form a pair. If you think of the structure of these operators, what this tells you is that I annihilate an operator at position k and I create another one at position k. So you could think of this as creation of a hole, and this is creation of an electron. Now, if I want to create a pair, I want to create two electrons, and so the way to do this is to do it in a BCS language by writing this down as delta and write this down as a way where I create a pair of the electrons. However, in order to have the lowest energy state, it turns out that it's advantageous for the pair to have a zero total center of mass, which is why I'm creating one electron with momentum k and another electron with momentum minus k. Now, the delta standing here generally is going to be k dependent, and that's the BCS gap. Again, Piers will probably cover tomorrow in more detail the structure of the BCS theory, and so in that case, just think of this as an advanced warning. Now, of course, so the Hamiltonian should be Hermitian conjugate. So what I should also do is to add a term that will look like delta star of k, where what I'm going to do is to create two holes, again with the total center of mass momentum, which is 0. Okay? Now, how many of you have seen this before? I just want to get a sense of how weird or, okay, oh, great. Right, I'm preaching to the choir. Okay, So now the part that I wanted to tell you is that there is a nice way to write this down in a way that would capture and hopefully bring similarity to what Jean-Noël talked about. And the way this is done is by noticing that the fermion operators with the same index anti-commute, right? So, well, okay, generally this would be delta of k minus k prime. And so what this allows me to do is that I could write down the first term of this expression by writing this, let me erase this part, by writing the first part equivalently as 1/2 summation over epsilon k minus mu, where I'm going to write down psi dagger psi, right? And then I'm going to add another term, which is going to be 1/2 minus epsilon k minus mu psi k dagger. Now the price I pay at doing that is that this commutator, so you see what I've done, this just tells you that a term like this is equal to minus that plus a constant. The constant is 1. And so in order to make sure that I leave everything invariant, I also have to add a constant, which is non-essential, of epsilon k minus mu. I may be missing a minus sign. So maybe there's a minus sign over here. The point is that this is just a constant that we add to the Hamiltonian, so it's unimportant. Now, the reason I write this in this form is because it's conventional, and to introduce, I'll use a capital psi, is introduce this as a vector that contains psi of k, psi minus k dagger in this form. And the reason one does that is because then the Hamiltonian as written can be written as a summation over k, and then one can write this in a matrix form where I write down psi and I have psi dagger standing on the right hand side, and sandwich in between it there is a matrix 2 by 2, right? And you see already the structure of this here. Over here I will have epsilon k minus mu. Over here I will have minus epsilon k minus mu. Now the term standing here would couple psi dagger to psi dagger. So therefore this would be delta, that depends on k. And this would be delta star, complex conjugate, that depends on k. Now there is this 1/2 that enters over here, right? And so what I should actually do is to write down here a factor of 1/2. Yes?
Do you want your capital psi on the right undaggered?
Do I want to?
Should that not be daggered?
Oh yes, you're right. Sorry, you're quite right. Yes. Thanks for that. Okay. Now this was developed by a Japanese physicist Nambu, who was working independently from a Russian physicist Gorkov. And so this conventionally is known as the Number Formalism, right? So now I'm going to put a check mark right here. Okay. Now the point of writing it in this way is because I could use the fact that any 2 by 2 matrix can always be written as a sum of, with some coefficients, of an identity and the 3 Pauli matrices, right? In other words, the identity plus 3 Pauli matrices form a complete basis of a unitary matrices 2 by 2. Or Hermitian matrices 2 by 2. So what this allows me to do is to write down this Hamiltonian in the following suggestive form. It's epsilon k minus mu multiplied by tau z. Now it's conventional to use taus instead of sigmas when you talk about the number formalism, just to be able to distinguish the spin, the matrices that act in the spin basis, versus this basis that I've introduced here. By the way, notice that I have silently not told you anything about spin. And the reason for doing so is because the first example we're going to study is actually a spinless p-wave superconductor. So if you want to generalize it with the spin, you could in principle put sigma over here. And because we are dealing with the triplet superconductor, I'm pairing the same spin with the same spin. So you could just think of the spin as a label, and I'm going to drop it and just assume that my fermions are spinless. Okay? Further remarks about what happens when you have spin will come. But for now, forget about the sigma Pauli matrices. These Pauli matrices work in the Nambu space. And now added to that, I can write this down as real part of delta of k multiplied by sigma x plus imaginary part delta of k multiplied by sigma y. And I've just told you that I'm going to use taus, and I violated my own promise, right? So it's going to be tau matrices, okay? Now, if you, all right, so I don't know how our short-term memory, do you remember what Jean-Noël told us this morning? What was the basis of the Haldane model? He wrote it in a suggestive form, and in order to define a Berry phase, he wrote the Hamiltonian h of k in the form that looked like this. Right, you remember this? And remember, there was a discussion that the spectrum, the energy spectrum, is just given by the modulus of this squared. No, sorry, by modulus of this, plus minus. And then this term is really what tells you about the eigenvectors, and therefore Berry curvature and Berry phase, right? Okay. So this is exactly what I'm going to do here. And notice that the vector h that I'm describing over here is given essentially by a vector that includes the real part of delta, the imaginary part of delta, and the epsilon k minus mu, which is essentially the kinetic energy. Okay? So modular replacing the sigma by tau, and thinking of this in Ambu space as opposed to spin space in which Haldane worked, you have identical structure, right? Now there are two ways how you could go about doing it further. So one way, which would be one-to-one, as how Jean-Noël presented it here. So the first way of dealing with this is that you think of this as a single particle problem, because this is indeed a single particle representation, right? What goes unsaid here is that the Hamiltonian I wrote here is the so-called reduced Bcs Hamiltonian. I've cunningly replaced, by doing Hubbard-Stratonovich transformation, the interaction term, and wrote it as a sum of bilinears. So the Hamiltonian as written is exactly solvable, right? And the solution of this is the Bcs wave function, of which Pierce is going to tell you tomorrow probably. The point I would like to make is that because we know the solution of this Hamiltonian, we could proceed exactly as was instructed by Jean-Noël this morning, where you define a Berry curvature as, I forgot if there is plus or minus I, but you define this as the solution. I'm going to use U as the solution just to keep the notation the same as Jean-Noël's. And then over here you have delta k acting on U of k. And then once you have this, you could define the Berry curvature, which one way to define this is it's a vector. Let's see how I would put this. Yes. So one way to do it is to write this down as actually the other way around. And so instead of using omega, I'll actually use the f mu nu that appears over here. And the notation should be suggestive if you remember the special relativity. That's how you write down the field tensor for the electromagnetic field in terms of the vector potential. Except, as I should stress, this is not a physical vector potential. This is a synthetic gauge field, if you wish. Sometimes people use this terminology, which is really the Berry connection. And so then the idea is that the Chern number can be defined by writing this down as 1 over 2 pi integral over two-dimensional space. To start with, by the way, so far I'm talking about, so this is my second bullet point, I'm talking about two-dimensional superconductors. So the reason why I'm integrating over 2 dimensions is because for now I would like to start with 2D, right? We'll come to 3D later on. And then standing over here, one way to write this down is to write this down as this f mu nu that depends on k, and that would give you the Chern number, right? So this is one way to proceed. Another entirely alternative way, which will give you the same answer, right? So another way of doing it is to define the same Chern number in a slightly different way, which I want to make sure I don't miss the factors, right, of pi. Yes?
I don't understand how you've gone from integrating an
So what in practice I do here actually is that, so I suppose that the way, this is what's actually being done, is that in practice one introduces the totally anti-symmetric tensor.
No,
Yes.
it's much simpler to see it. I mean, the Berry connection is selected lives in the xy plane.
Mm-hmm.
Okay? So when you take the curl of it, it will point in the z direction.
That's right.
Actually, f mu nu is always in the z direction, and it's just the z component of this Berry connection point.
Yeah.
So it is a scalar times the z component, which is perhaps not so evident here in this mu nu representation. But remember that mu and nu are just x and y, so there's only one component.
Yeah. Right. So this is, so if you want to be pedantic about computing the indices, you could do this. The reason being is that this is a totally anti-symmetric tensor from its definition. So if I change mu and nu, this is going to be 0. I mean, it's going to change sign. So is this one, right? So that's one way how you could view it. Conventionally, people don't write this down. And then if you want, you could keep here the index. So one way to do it is to keep here an index, whatever lambda, and write this down as mu nu lambda. And now this is where what Mark just said maybe perhaps more transparent. So remember, so what is epsilon mu nu lambda? It is a totally anti-symmetric tensor which is given 1, well, if it's in the order 1, 2, 3. So if I choose mu and nu to be kx and ky, or xyz, right, kx, ky, then that means lambda can only be z. Yes? So explicitly, cz is going to be 1 over 2 pi integral over dkx dky multiplied by fxy that depends on kx, ky. Okay? Now, there's an alternative formulation of writing this number, c, which is entirely equivalent, which amounts to the following. You still integrate over two-dimensional space, but what you do is that you write down a triple product of dkxn cross dkyn, where n is a unit vector, which is defined right here. Right? So to be specific, n of k is really what I've just written over here. It's my h of k divided by its modulus. Now this is, let me see if I could justify. So it turns out, first of all, you could rigorously prove that this is equivalent to this. For the specific case where the Hamiltonian is of this form, in other words, you're describing a particle that moves in an external field of strength h. Then defining Chern number in a standard way that Jean-Noël introduced is totally equivalent to doing it this way. Right? Now, as far as I know, the first way where this was done by, pardon me, by Belavin and Polakov, who are high energy theorists, but the title of their paper is actually Topological Defects in a 2D ferromagnet. So what they actually had in mind is a two-dimensional ferromagnet. And in their formulation, they didn't have kx and ky. It was formulated entirely in the real space. And the Chern number was given 1 over 4 pi integral over d2x, where what was written is n dxn cross dyn. Let me see if I can use a different chalk. All right. So now the structure of this, right? So first of all, it turns out that the number c is quantized in integer values, right? And the reason why that happens is that, let's try to analyze this from the same phenomenology that Jean-Noël told us about. If I think of the vector n, right? Vector n is really a map that takes either x and y in the case of the real space, or if you wish, kx and ky, and it maps them onto an object, n of, let's say, xy, that lives on the unit sphere, right? Unit sphere, because this is, I define this to be as a unit vector with 3 components, right? So therefore, formally, mathematically, it's a map from R2 into S2. Or if you wish, if you think of periodic boundary conditions, then maybe it's a torus. Okay? So now the question becomes, right, so how do we analyze this map? There is one way, which is called stereographic projection. It's not used for cartography for reasons that you will see shortly. But so what you do is that, let's say you have our planet and you want to make an accurate map. Well, one way to make a map is to, place the sphere gently on a paper. You should really do it not with the Earth, obviously, but with the globe. So put globe on a newspaper, and that point, which is the South Pole, call it the origin. And then what you do is that you start from the North Pole, and you draw through any point on a sphere, so let's say somewhere over here, right? You draw a ray until it crosses somewhere on that plane. This is called a stereographic projection. What it does is that it identifies every single point on a sphere with a point somewhere on the plane and vice versa, with one exception, that the North Pole is kind of tricky, because technically if you want to describe the North Pole itself, you have to draw a ray that starts from here and goes parallel to the plane. But when I say parallel, well, it's not entirely identified because I could choose an arbitrary angle phi, and this would still correspond to the North Pole. So therefore, what this means is that the points at infinity on this plane, everywhere on the infinity, they are identified with the North Pole of the sphere. And there is, believe it or not, thousands of people who think that this is how our Earth looks like, and they call them, say, flat Earthers. So there is a giant wall of ice that corresponds to the North Pole. Now, for some weird reasons, they like to flip this around. So they put this as a South Pole. So the Antarctica actually describes the giant wall of ice, which is sort of far away, and you can never reach it because it's so far away. And then everything you see essentially corresponds to those parts of the Earth which you can actually reach, right? So the South Pole is unreachable, and it's technically everywhere around you. Okay, so nobody in their sane minds, except for mathematician, would use a map like this. But what it allows you to do is essentially to map a two-dimensional plane onto a sphere with the statement that the infinite points of the plane are actually mapped onto one point, which is the North Pole. Okay? Now, mathematicians call this compactification because the manifold you're starting from, which is R2, is not compact. Compactness is a tool in mathematics to describe whether an object is, roughly speaking, finite or not. I'm not going to give you a formal definition of compactness. But the point is that you could kind of have a sense that an entire infinite plane, you could start somewhere and this line can never end, whereas somewhere on the surface it's bound to come back to initial point, and in some sense it forms a compact surface. So as a result of this compactification, what we could do is that to think of this map N as secretly a map from S2 into S2, right? Now, what this then allows us to do is to fall back onto what Journal told us about the homotopy. So this appeared already twice, I think, in his lectures. Remember, there was this object which was written like this, where the S2 in the parentheses corresponds to the target manifold, which is where I'm mapping onto. And the little 2 that stands over here corresponds to the base manifold, where I'm starting from. And the result from the mathematics is that it's defined by a group and is given by a group of integers. So what this tells you is that arbitrary map that you could imagine of this kind falls into one of the classes that are labeled by an integer. There are infinitely many of them, and if you have any two maps, you could ask yourself whether they're equivalent in the sense of smooth deformations. So if I have a map, can I smoothly deform it to give you another map? So let me see if we could do this. Imagine I have a sphere, right? And let's say I have a map that looks like this. Sometimes this is called an identity map or an Euler map. So at each point on a sphere, I take a point and I put it somewhere there. The question I would like to ask you is whether this map is smoothly connected to this map. Where again, this is a sphere. So are these two maps equivalent or not? Any suggestions? More or less. So the sphere remains orientable. So let me give you an example where you will see how they are. So this is in the case of S2. Let's see how this works in the example of S1. I have a circle, right? And the question you could ask is that if this is a unit circle, is this map equivalent to this map? Okay, so now I want audience participation. Andries gave such a passionate speech. Right. So, yes. Oh, great, fantastic. I love Pierce's idea. Okay, so let's start from the bottom. So who thinks that the bottom map from a circle to a circle, that these maps can be smoothly connected? Please raise your hands. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Roughly, okay. How many people thinks that these two maps are not equivalent to each other? That I cannot invert, well, turn the circle inside out. So I have 1, 2, 3, 4, 5, is it 6? Yeah, maybe 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right, so either my count is off or we have a perfect balance. All right, so let's do an exercise. Remember, you've seen these pictures before. They were drawn by Jean-Noël where there was a discussion of what smoothness means. Let's try to globally rotate all of these arrows by the same angle. I could take this arrow, and in fact, let me do an intermediary step. Let me go from here and rotate all of them counterclockwise by 90 degrees. I will end up with something that looks like this. Now, you've seen this picture. When Jean-Noël wrote this, right, this was called a vertex. And the question was whether a vortex looks similar when it's written like this, and we realized that actually they're the same, you just have to rotate. Now let me rotate this by 90 degrees more, which means I'm just gonna rotate more. So what I've done here is to rotate it by 90 degrees. I'm gonna do it again, and I'm gonna end up with the picture like this. Yes? So you're convinced that now I can do it smoothly, right? So if you imagine smoothly, if 90 degrees, imagine I create a very smooth map. That's how homotopy actually defines in mathematics. You define a very smooth way as a function of time, where I slowly rotate each spin, and eventually, adiabatically, I could smoothly move from here to there. Yes, question?
Is it too naive to imagine that these are physical objects, and in one case you're just sort of pulling it up like Play-Doh, and in the other case you're kind of just pushing it together?
Well, so I find it more intuitive to think of this as a flow of liquid, right? So you have an object, and so that's where the idea of vorticity actually comes from. You should think of this. The mathematical definition of this is so-called vector field defined on a smooth manifold. So this vector field lives somewhere in a space defined by a sphere, well, in this case, a circle. And then you could think of it as each arrow as being, for instance, a direction of travel. So it could be an ant that travels perpendicularly, or maybe tangentially, or maybe inside. So yes, you could think of this also as a strain tensor. Well, not tensor, I don't want to use this terminology, but let's say a strain in the material, right? So you could physically indeed thinking of smooshing the circle or expanding it, right, if that's easier. Or you could imagine a shear deformation, which is what this would be. Okay, now let's go to the S2. So raise your hands, those of you who thinks that I can smoothly go from here to there. There is one. Can I smoothly go from here, from left to right for the case of the sphere rather than the circle? So there are some clever people who sit in the pose that, there is a famous Rodin statue that looks, how is it? I think it looks like this. So I can't say if this is the hand up or not. So raise your hand clearly if you think this is doable. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, roughly 10 or 11 people. Okay, how many people think this is impossible? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, majority thinks that this is impossible. All right, so now, if this were possible, I ought to be able, in principle, this is a hand-wavy argument, not a mathematical proof. I ought to be able to go through the intermediate step like this and have all the vectors lie somewhat tangential to the sphere, okay? This is called combing the sphere. And there is a theorem in mathematics called the Hairy-Ball theorem. Mathematicians are inventive. Hairy-Ball theorem that tells you that you can never comb a sphere without at least 2 hairs sticking out, okay? You could try, and you could see why most of us, well, unless we, well, 2 options, right? We could be bald, but if you're not, but if you're not bald, then usually there is a vortex right here, right? Where in the center of the vortex, actually the direction of the hair isn't lying flat. It tries to go, well, you know, it kind of sticks perpendicularly, right? Now, by the way, proving the theorem, the Hairy-Ball theorem, is not that simple. If you want to prove it for under most general circumstances, it's a major piece of mathematics that requires the knowledge of so-called Theorem cohomology. But the proof roughly goes by showing that you cannot go from this map to this map by defining the so-called index of the map. This index was defined first by a mathematician Brouwer. Actually, I'm not sure how you pronounce his name properly. So if he was German, this would probably be Brouwer, but I'm not sure. I'll have to look it up. But it's sometimes called a Brouwer index of the map. And guess what? That index of the map is what I've just defined by this number C, which secretly we know is the same as the Chern number. So the Chern number of the object on the left is C equal +1, and the one on the right is C equal -1. And the statement that I cannot smoothly go from one to the other is equivalent to saying that I cannot smoothly connect 2 objects that have different topological invariant. Okay? I've seen a wonderful picture that Mark showed me, where it's taken in 1967, where there is a lecturer here in Cargese who's teaching on the beach that's now unfortunately not sandy anymore. Now, what surprised me most about this picture, not the fact that people are sitting in the bathing suit and, you know, everybody's wearing short and relaxed, but the fact that the board is only slightly bigger than this, okay? So I have no clue how I would have worked in this situation, because you see, I'm running out. I have to erase something. All right, so what have I done so far was to introduce this topological invariant for the 2-dimensional superconductor. Now, if you ask me, okay, that's great, you've drawn some picture of hairy balls, but sorry, no pun intended. Oh my God. All right.
It's on record.
And that's how you get yourself in trouble, okay. So I've drawn some pictures, but what does it actually mean physically if you start from something like this? So think about this way. If I look at what this vector looks like, right, there is one ansatz that I can suggest where I take this n vector to be kx, ky, and for now let me leave this epsilon k minus mu to be like this. Now look what it means, that when I'm sitting somewhere on the equator, so let me define an equator to be an object where this is exactly 0. Then I have my vectors that are pointing respectively in the x and y direction, basically out of the plane. So which means over here, they're kind of pointing like this, right? And they point out like this. Now let's see what happens on the poles. So the poles, remember, it's useful to remember the stereographic projection. The south pole in the picture as I've drawn it corresponds to the k equals 0. Remember I said that we're going to choose this as our basis where k is equal to 0. Which means when k is equal to 0, this is at the south pole, this is going to be 0, 0, minus mu. Now let's look what it looks like at the north pole. At the north pole, remember, in the stereographic projection, that means k goes to infinity. Now in practice, you're going to object saying that we actually start from a Brion zone, and in practice my k is actually finite. But we're going to, because we're using essentially a long wavelength limit, we are thinking of 1 over lattice spacing as the being ultraviolet cutoff, meaning we're never going to think of the wave vectors this large, so we're going to approximate them to be infinity. Now when this is infinity, right, this means no matter what this mu is doing, the k squared over 2m is always going to overwhelm it, right? Now remember that these are unit vectors. They're defined, I have to divide all of this by the modulus of the vector itself. So actually, if this is n, if I think of the unit vector, then this is actually b minus sine of mu, and this is going to be 1, right? Because I'm dividing by the, you see what I've done here? I'm dividing by the modulus of the same vector. So if this is infinity but points up, when I divide this by, I get a unit vector that looks like this, which means at the bottom over here, right, at the south pole, depending on the sign of mu, I either get a picture like this. So let me see. So if mu is larger than 0, this is the picture I have. On the equator, I have the arrows pointing out, right, going like this. At the south pole, according to this points downwards. And at the north pole, it points up. And you could interpolate and show that anywhere in between, this would actually look like this. Now, on the other hand, if I choose mu to be negative, the picture is going to look like this, where it's going to point up at the south pole because of this minus sign. It's going to put up at the north pole, and maybe somewhere over here it's going to point, in the direction like this, right? Now, what you could show is that if you were to compute the Chern number of this object, as illustrated here, you would get, in this case, c that's equal to +1. If you do it in this case, you would end up with the 0 Chern number, because this map is the same as a trivial map where everything just points up, because you could smoothly deform the stuff in between on the latitudes, spanning the north and south poles so that everything kind of points up. Make sense? So one way to think of this as the wrapping number, right? Remember the basketball bag analogy? So this is where you've placed the ball on the bag and let it roll, and it just didn't get there at all. This is where the bag is entirely around the ball. I love that analogy. Thanks, Janael. This was great. Okay, so now what this tells you is that the topology of the superconductor isn't just dependent on the real and imaginary part of the gap. By the way, what I've secretly done right now was to describe for you a superconductor that has the following structure: kx plus iky. Right? Because remember that this is the real part of the gap, and this is the imaginary part of the gap. And I've thrown away the prefactor delta naught that I should have put here. In the end, it doesn't matter, right? So that's the superconductor we're trying to describe. Sometimes people call this P plus IP. So the P plus IP superconductor, based on what I told you, may or may not have non-trivial topology, depending on what the chemical potential is doing. When the chemical potential is positive, I end up with a topologically non-trivial solution. Where it's negative, I end up with a topologically trivial solution. Now, for those of you who have heard maybe talks on AMO, on optics or atomic physics, when they go through the so-called, help me here, resonance, what is this called? Feshbach, that's right. When they go through Feshbach resonance, typically by tuning with the magnetic field, the splitting between hyperfine levels, they can tune the effective attraction between the molecules, and they could smoothly go from the limit where the attraction is positive or attraction is negative in the sense of the chemical potential. This limit over here is often referred to as a Bcs limit, and this limit over here is often called a Bec limit. In a sense, this is a strong coupling limit where the two molecules form tightly bound pairs, and whenever you have local object, right, where you've bound them together and they're local, you could always assume correctly that this is a trivial phase of matter, right? Because it's trivial in the sense that you could try to cause grain more and more, but because each two Cooper pairs have such a small radius that you could eventually split your material in half, and the two halves would both be trivial, right? By contrast, in the Bcs limit, Pierce told us about the concept of the correlation lengths. That's roughly, I mean, one shouldn't take it seriously, but picturesquely, this is the distance between the electrons in a Cooper pair or atoms in a superfluid of helium-3. And when that distance gets large, that's the weak coupling that corresponds, in this case, to positive chemical potential. Now, where the topology, so you could ask yourself, great, well, how will I ever see that this is something topological, right? So for the experimentalists in the audience, what would be the experiment that you would devise in order to demonstrate that there is a non-zero Chern number here, but not here? So Jean-Noël proposed that you could kind of go through the tick mark. First, you have to make sure that your phase is fully gapped. So let's check first whether the superconductor is actually fully gapped. So the way you would do this is by looking at, let me see. I don't need this left-hand side anymore. So you could look at the solutions of the Hamiltonian, right? And as Jean-Noël told us today, they're given by this epsilon plus minus, which is a function of k, which is equal plus or minus modulus of this h of k, right? Which is nothing else but plus or minus square root of epsilon k minus mu squared plus delta, which itself depends on k squared, right? So if I take the specific example of the p plus ip, so if delta is proportional to kx plus I ky, it would follow that epsilon plus minus of k is plus or minus this object plus modulus of k squared. Now remember that when you do this in a superconductor, the pairing takes place at the Fermi surface. So the k isn't just sitting somewhere at the gamma point, but it's somewhere on the Fermi surface. So as long as the Fermi surface does not actually go through the gamma point, it typically does not, this is basically the size of your Fermi surface. Now, independent of what mu does and how k exactly depends on epsilon k, you could see that there is always a gap over here, and I should put delta naught modulus squared, that always enters into this expression. Which means that if you were to draw what the spectrum looks like, right, you would typically have a situation like this, where this gap over here would be twice delta naught times kf. Conventionally, people put hats over here, so these are unit vectors. So then you don't have to worry about this, because that's just a modulus of a unit vector, which is 1, and then this is a neater way of writing it where you don't have a weird prefactors. Yeah? So the system is indeed gapped. Now remember, the second experimental signature that you would see, well, this is not yet a proof that this is topological. Depending on whether nu is positive or negative, the spectrum by itself does not tell you anything, as Jean-Noël emphasized. You actually have to compute the Chern number to convince yourself that this is actually topological. So the second thing is what was referred to as a bulk boundary correspondence, whether or not there are some chiral states or something funky happening on the surface. So I'll give you a sketch. I have detailed notes that will be uploaded on the website where you could see the detailed derivation, but I'll give you a sense of what we're going to do. We're going to construct the following geometry. Let's take a ring. So this is two-dimensional, remember. So this is not a torus. I'm just drawing a flat base, where everywhere around here, I'm going to take mu to be positive. Inside, I'm going to take it negative, and outside, I'm going to take it negative. So based on what I told you, everywhere inside, I have a Chern number, which is +1, which is topologically non-trivial. On the inside and on the outside, I have a trivial regions, right? So let's call this region 1, 2, 3, okay? Now, the exercise of doing this calculation is to essentially find what is the wave function that describes, that lives on the surface over here. Now, the reason I draw a circular geometry is because I want to use polar coordinates. It's purely a trick to make the calculation more feasible, but if you insist to make this some weird shape, you could still do it, and you could still find the modes, it's just the calculation is going to be lengthier. So let's use a polar coordinate, right, where this is r, and there is an angle theta, And let's see what we could do. Now, the Hamiltonian as written, I almost erased it, is 1/2 psi dagger times this. This was my Hamiltonian over here. I could alternatively formulate it in real space. And formulate it in real space, I could write this down as, let's do it properly. Let's do this as the integral over two-dimensional space, where this object now lives in R space rather than in K. And this matrix would now basically correspond to a kinetic energy term that I would have to put in here. And because in the end everything just depends on the sign of mu, let me assume that the dependence on K is very small. For instance, you could do it if the mass of quasi-particles is very big, or if the chemical potential mu is much larger than the size of the Fermi surface. Because remember, this is going to be at most kf squared over 2m. So for instance, in a helium-3, where we're going to go next, the Fermi surface is tiny, it's near the gamma point, you could safely forget this. So it's going to simplify our calculation if I could write down this as minus mu plus mu. Now, in real space, what used to be kx plus I ky is going to look like a derivative, dx plus I dy and dx minus I dy. Now, written this way, this is nothing else but a hidden form of the Dirac equation, because what I have is the derivative multiplying the Pauli matrices, right? Except the mass term, which lives here and here, right? And this is written sort of in the Nambu notation. Now, the way this calculation proceeds is by doing a Fourier transform into polar coordinates, where that same matrix basically becomes minus mu and plus mu over here. And over here, well, it should be, by the way, this d should be multiplied by a gap, and this should be multiplied by the gap. Well, gap is real number for now, so I will have some delta naught. And in spherical coordinates, this could be written as I d theta over r, and this is going to be d naught dr plus I d theta over r. So it turns out that you could generally write this down in this form, and there is a general, and there is e to the power I theta over here, and e to the power I theta over there. Maybe I should write this bigger. I'm sorry for writing it in a small font. So what's really of interest here is this operator. So what I said in words is that dx plus I dy with imaginary time could be written as minus dr plus I d theta over r multiplied by I theta. So this is, you could just do it by hand, or you could look it up in any mathematics book. This is just how the derivatives look like in the polar coordinates, okay? And now the logic becomes as follows. It's essentially a one-dimensional problem now, if you think of R going from left to right, and it's no more different than solving a single particle Schrodinger equation, except here it's really not a Schrodinger, but more like a Dirac equation, with the boundary conditions between regions, right? You've all done some sort of scattering problem, or the problem with a double well potential, where you divide the problem into the three regions, 1, 2, 3, and you solve it in each region, and then you match the boundary conditions, right, for the wave functions. The calculation proceeds in a similar way, and the goal is to find what happens on the boundary over here and over here. So I'm going to call this to be R1, and this radius to be R2. And our goal is to find what the solution is. Now, I won't go essentially it's a first order partial differential equation in terms of dr's and d theta. So I won't give you the sort of line by line derivation, it's in the notes, but I'll quote the final result, that if you actually, so it's useful to look for the solution in the form where chi L of theta, so chi is so what I'm solving is the Hamiltonian where h of chi is equal E of chi, where E is some unknown energy, and I'm looking for this solution where r, little r is equal, let's say, to R1, and here r is equal to R1. So I'm looking essentially at chi in this entire region, but fundamentally I'm interested in the eigenvalue solution here and eigenvalue solution here. And it turns out that this chi L, that the solutions are numbered by integers, and they go like e to the power 2l plus 1 theta divided over 2. And then there is an ansatz, which generally it's a complex function, so I could put it as fr plus I g of r and f of r minus I g of r, where f and g are some real unknown functions. Yes?
Sorry, I think I missed something here. What's chi developed in?
Right, so chi is an unknown solution of the Schrödinger equation with the Hamiltonian h given by what I've just written, well, what's written over here.
Oh, okay.
Right? So chi, by definition, so h is a Hamiltonian matrix, which is 2 by 2. So my chi is going to be a vector with 2 entries, which I've chosen to parameterize like this. The reason why they're written, with this is plus and this being minus, is because I keep in mind that the initial psi, this field operator that I've introduced, actually has a form. Remember I wrote this earlier, that it has a form of psi of r and psi dagger of r. So the two field operators are Hermitian conjugate of each other, which means the two solutions are Hermitian conjugate of each other. So I've chosen f and g to be real, therefore this has plus imaginary I and this has minus imaginary I. Now the part that I really want you to pay attention to is the fact why I wrote this prefactor in this way. That's a statement that when I go around the full circle, because remember this is defined in real space and this is a polar angle, that when I start from here and I go a full circle and I add a factor of 2 pi, according to what's written here, this is equivalent to stating that chi L of theta plus 2 pi is equal minus chi L of theta. So I've chosen the anti-periodic boundary condition, and I explained, I should have done this earlier, why this is the case. So this is not a, so let me see. Let me keep, we'll come back to the short numbers later, but for now I'll just keep this, and we don't need this part anymore. Okay. Now, what I've secretly done without telling you is that obviously when you choose your solution for the wave function, you want it actually to be periodic. So normally what you want is to have psi of theta plus 2 pi to be equal psi of theta. However, what I've done, I've made a map from here to psi tilde of theta multiplied e theta over 2. Now if you do the same, you will find that therefore phi tilde of theta plus 2 pi has to change sign minus psi of theta in order for this function to be periodic. Right, so this is a pure mathematical trick where I've changed the boundary condition by multiplying this by I theta over 2. And the reason I did this is because when I was solving this equation, what I was trying to avoid is having this e to the power I theta present over here. It makes the solution much more complex. It means that now I have to look for a differential operator that actually depends on some weird phase as I go around. So in order to erase this e to the power I theta, remember that this matrix is multiplied on the left and on the right. So I start with something like this, and it has e to the power I theta. And remember that multiplying this matrix on the left and on the right, there is psi and there is psi. That's my Cooper pair formation. So what I've done, I've absorbed what I said. I took this factor I theta, and I erased it, and I wrote this as I theta over 2 on the left, and e to the power I theta over 2 on the right. And then I took this object and say, okay, great, now I can just replace this and call it psi tilde. So what I'm actually doing is searching for the solution of the equation in this modified form, and the price I have to pay is that my solution has to be anti-periodic as I go around the circle. In the end, I'm going to multiply it by I theta over 2 and restore the periodicity. So don't worry, physically it's still okay. But in terms of solving for the solution of this chi, The reason it has this weird antiperiodic boundary condition is because of what I just said. So therefore, this has to be a half integer for this to work, okay? Now, if you look at what the solutions are in the regions 2 and the regions 3, what you will find is that essentially, again, this is without proof, but I'll show you that if you look at solution where R approaches R1, that this is basically going to be proportional to an exponential of minus 1 over delta, integral from R1 to R multiplied by integral of mu of R prime, okay? So what I should have said earlier is that what I'm doing is the same trick as the Jakiev and Rebbe, which is what Journal told us earlier. I'm allowing the chemical potential not to be constant, but to change smoothly. I kind of indicated it here by saying that mu, chemical potential, has to be negative inside of the annulus, positive in the annulus, and negative again outside. So what I really mean by this is not an abrupt change, because remember, I want to have a smooth, well-defined wave function. What I really mean by this is that if I start from the radius and I go outwards, right? This is my R1, this is my R2. That therefore, when I look at the value of the chemical potential, it's better be negative in this region, then it's smoothly gonna go through, it's gonna be positive, and again gonna be negative. The topologically non-trivial region is in the middle, that's this part, where the chemical potential is positive. And what I'm trying to do is just like Jakiev and Rebbe, to look for the solutions which happen over here and over there. And essentially what the solution tells you is that as a function of the coordinate, it actually looks in a following form. You see, this is a definite integral with the upper bound R, which means this goes roughly as an exponential of minus mu of R divided by delta, right? And you see that depending whether the mu is positive or negative, I have to be careful to look for the solution which has the correct form. So here I'm solving it in this form where mu is positive, which is why this is a well-defined solution. And the key point to note is that it's going to be exponentially localized near the boundary. So the solution that I've just found is going to be exponentially localized within a small circle of in this vicinity. And the radius of localization is going to be given by 1 over the gap. Right? That's one way how to think about this. Now you could do the same analogy and look at what happens in a solution where R is equal to R2. And you find that in this case, it's going to be, if you do everything correctly, that the integral is going to go from R2 towards outside, except there's going to be a plus sign instead of minus sign. And that's okay because my chemical potential is negative in this region once I'm outside. And so what you will find is that the solution is exponentially localized in this region, which is the outside of the circle. Again, with the radius, which roughly depends like 1 over the gap, right? So that's the logic of this argument. So now the interesting part comes from the fact from realizations that if you actually look at the solutions carefully, you will find that there are 2 energies that are associated with this solution and this solution. And the energy in the 2 cases is actually given by 2L plus 1 over multiplied by delta divided over R2. And the solution of this one is going to be E, which is 2L plus 1 delta divided, sorry, this is over R1 and this is over R2. And the first one is negative, the other one is positive. So what this actually tells you is that the 2 solutions that correspond to this, they seem to have opposite energies. And if you were to plot what these energies look like, right, you would conclude that basically you will have one solution that if you keep L to be positive seems to be doing this, and the other one would seem to be doing that. However, what turns out is that only positive values of L are important for the reasons I'm just about to discuss. And so what happens is that you should really consider only the solutions that correspond to the positive energies. There will be two of them. One of them will be over here, and the other of them will be over there. And the reason I'm drawing discrete crosses and discrete circles is because the energy comes in discrete intervals in the increments which is given delta over R. So this difference between the two energies over here is of the order of delta over R, where capital R is either R1 if you're looking at the solution on the inside circle, or R2 if you're looking at the solution on the outside circle. And the point is that because this is half integer, it never crosses zero. So you have a solution which, you know, the smallest number that you have is 1/2 delta over R. Well, actually 1 delta over R is written over here, okay? So the point is that in the end you end up with two Majorana, oh sorry, I spoke too fast, with two modes, two edge modes. They're chiral because if you actually look at what the solution, you know, what solution they're multiplying, it turns out that the first one over here, because of the form I've chosen, looks like I2L plus 1 over 2 theta. And the other solution looks like E minus I 2L plus 1 over 2 theta. So if you imagine what happens when you increase theta from 0 to pi, in one case the phase of my solution increases together with theta, the other one goes opposite direction. So therefore these modes, one of them goes counterclockwise like this, and the other one goes clockwise in this direction. So you end up with two chiral modes that only move in one direction. And so for clarity, the mode that moves in the, you know, this is the one that moves in the opposite direction, right? So this is, if you wish, the counterclockwise, and this is the clockwise mode. They each live on the boundary, and the reason why there is exactly one mode on the boundary is the so-called bulk boundary correspondence, of which Jean-Noël spoke before. Right? So formally, what you should think of is that the Chern number is +1 over here, but it's 0 in this region, and it's 0 in this region. And the idea is that the number of edge modes, so this is a formula that Jean-Noël had on the board. That the number of edge modes was given, in this case, the Chern number, whatever invariant you have, in region 1, let's say, minus the Chern number in region 2. And in our case, this is 0, and this is +1, and so by modulus, that difference tells you about the number of edge modes. Same happens when you look at the region 2 and region 3. They differ, the Chern number differs by 1, therefore there is exactly one chiral mode. Now, the funny thing about superconductors is that if you look carefully at the energy spectrum, in some sense you see that there is a weird overcounting, because the so-called spectrum of the Bogolubov-de Gennes Hamiltonian is exactly reflected around 0. And there is always a positive band, right? And there is always a negative band. Now it turns out that the reason why there is this symmetry goes to display so-called particle-hole symmetry of the Hamiltonian. It tells you that if I started with my Hamiltonian and I did what the particle physicists call the C transformation, I took all creation operators, psi, and I replaced them by annihilation operators, then the Hamiltonian actually remains symmetric. As a result of this, that means that all energy spectra are kind of going to be doubled, right? And so often, you know, you don't have to think about both positive and negative. Often it's sufficient to consider only the negative branch or only the positive branch, right? So this is a generic property of Bogolubov-de Gennes Hamiltonians, that the energy spectrum is always symmetric around 0 energy. Therefore, what happens that in these solutions that we found, both these solutions correspond to a specific energy that, as written over there, is 2L plus 1 delta divided by R. And you could choose the sign to be either positive or negative, but you shouldn't really consider both. So what this tells you is that really the solution you discovered is kind of half of the degrees of freedom that cover this entire spectrum. They're either positive or not negative, but cannot be identified at the same time. So what this tells you is that if you look formally at the solution, this tells you that chi L dagger is actually equal chi of minus L. Or another way to say it, because of how this is formulated, at the chi at positive energy is the solution of chi at minus negative energy. Right? So when you do particle-hole transformation, you just replace particle by a hole, you change E to minus E, and you flip from this branch to that branch. The particles that have this property are called Majorana particles. It's a particle that is kind of self-conjugate of itself, right? And so the moral of the story is that the edge modes that live on the sides of this P plus IP superconductor, they are not just chiral, but they're chiral Majorana modes. And the Majorana are these weird particles that its own antiparticle, right? So Majorana initially formulated this keeping in mind the physics of neutrinos, because neutrinos can only be left-handed and not right-handed, and the question was, why is that? And so this was an attempt to try to describe perhaps something that might be happening in that case, right? But here we're encountering Majorana particles in the context of condensed matter. Now, what's really captured the imagination of the condensed matter physicists in the past maybe 10 years was that you could try to actually capture these Majorana particles. And the idea was that if I take this, the spectrum as written, I face the problem that the energies of the particle is always positive. So when I do this transformation, E goes to minus E. So technically, I cannot quite capture the particle because it flips its energy. And if I'm only allowed to keep positive energy particles, then its counterpart is always out of reach. So the idea is that if I could somehow make the energy E here to be 0, that would mean that now I would have just one particle at 0 energy, I'm going to call it gamma, for which gamma dagger is truly its own antiparticle. And that would be a true Majorana, but that can only happen if it has 0 energy. In the context of neutrino, that would mean it must have a 0 rest mass. It's not allowed to have a mass, right? So how can we do that? The idea is that what you could do is to try to thread a flux through here. So it turns out that if you thread, if you take and you thread a flux, which is H over 2E, through this, through the annulus, through the normal region, the one that's not, well, when I say normal, topologically trivial one. What will happen is that the idea of the flux, I'm giving you a hand-waving argument, but the details are in the notes if you're interested in a mathematical description. What it does, it swallows up this factor of I theta over 2, because the property of the flux is precisely that when you thread a vortex, it exactly absorbs the phase, and so now there is an extra phase appearing here. So what this would mean is that now I don't have to write down this I theta over 2. Those factors are already captured by the fact that I inserted the flux. The way it manifests itself is that I don't need to introduce psi tilde, and I don't need to impose anti-periodic boundary conditions. Instead, they will actually remain periodic. So what this means is that in my solution, instead of requiring that this should be negative of itself when I go back, I enforce periodic boundary conditions, which means instead of half integer, this 2L plus 1 over 2 instead becomes an integer, e to the power I and theta, right? So so I said it in words, before you get more confused, let me write this down in words on the board. So when a flux, a unit flux, so phi equal H over 2E, is threaded, it absorbs the factor e to the power I theta, because that's the vorticity of the flux. And so as a result, that means that my chi of theta plus 2 pi now is periodic. which means when I look for solutions, that means that my ansatz is that my chi of theta goes proportional e to the power I n theta, where n is a positive integer. Positive because of what I just said, you don't need to consider both positive and negative. Now what that means is that when I now draw the spectrum, energy, instead of energy being given 2L plus 1 delta over R, my energy En is just n multiplied by delta over R, where n is integer. And so there is one solution, which is right when I took n to be exactly 0, which means that now there are still discrete spectrum of these quasi-particles, and still you should think of this branch rotating clockwise and this branch rotating anti-clockwise. But now there is one solution which is kind of right here over here, and it's really doubled because one of it comes from this branch and one of it comes from this branch. So there are actually two Majorana particles. Both of them have 0 energy, but one of these particles is trapped here and the other of them is trapped over there, right? Now, once that idea has been realized, it was immediately suggested that if you actually take a physical flux and you thread it through a type 2 superconductor, right? So what I just told you here is a thought experiment. You take a unit flux, you thread it. But as Piers explained to you, fluxes are naturally quantized in a type 2 superconductor. It likes to have a flux which is pinned, and it's exactly unit flux. So therefore, the idea which was formulated by Grigory Volovik in '99 and shortly afterwards by Dmitry Ivanov and also Nick Reed and Green, who was, I believe, his postdoc or his associate. So roughly around on the turn of the century, 1999, 2000, the set of ideas emerged that if you take a P plus AP superconductor, assuming it's a type 2, you thread a flux through it by applying external field. There will be regions with the unit flux, and around those regions you will have quasi-particles like this, which are going to be pinned inside of the vortex. So the picture you should have is that you have this two-dimensional superconductor, and you thread a bunch of vortices through it. Each of them is a unit vortex, and in the core of each of one, right, the idea is that you have a normal core where the field is expelled, right? That's given by the penetration depths. That inside there's going to be a particle which is going to be a Majorana that is going to sit there. So what I want you to realize, and this is a recurrent theme in topological superconductivity, is that generally the statement is as follows. The bulk boundary correspondence tells you that if you have a vacuum bordering a superconductor, on the surface there's going to be a dispersive Majorana mode. Not necessarily at 0 energy, it's going to generally be dispersive and chiral. Right? Now what you do is by applying external field, you could then pin that Majorana to be at 0 energy. So often people confuse these two. Really you should think of the latter case as a Majorana 0 bound state, whereas the first one is just a dispersive Majorana which has a spectrum, it has a finite energy. Right? So the reason why this is also intriguing is because Majoranas have very weird properties in 2 plus 1 dimensions. So Majoranas, if you think of them in a plane, as in here, it turns out that if you take one Majorana and you thread it around and you put it back where you came from, you actually end up with a non-trivial phase of pi. Right? To see why it's non-trivial, remember that if this was a pure boson, nothing would happen if you move it around. Now let's see what happens if you could guess. So what happens if this was a fermion? Let's say I have two fermions there on a plane, and I'm taking one of them, let's make them different colors. Can you all see if I do a tabletop experiment right here? So this is my one fermion. I take the other fermion, and I draw an arc, and I come back to the same place. If the two particles are fermions, what is the phase of the global two-body wave function that I'm going to pick up? Yes, I hear pi. So the answer is actually 0. Because remember, the statement about the change of sign of the wave function is when I swap the positions of the two particles. So if this is R1 and this is R2, swap would mean this. So I swap them one, the particle change sign, right? Because this, remember I started where the white chalk is on the right of the green. In reality, they're indistinguishable particles, so the color is misleading. But the point is that once I put it here, now my chalk is on the left of the green. The particle has changed sign. Now I do another half circle motion, and I've changed the sign again. So nothing actually changes, whether there's a bosons or fermions. The weird thing about Majoranas, I'm not going to prove this, is that if you actually move one particle around the other, you pick up a minus sign. The particles that have this property generally are called anyons. And to make things interesting, this is so-called non-abelian anyons, because generally if you move them in some particular way, you end up not just with minus sign to the wave function, but you actually change the spinorial part of the wave function. So what this amounts to is that if you could somehow manipulate this particle and move it around, now you could see why this is difficult. You would have to have access to magnetic field at the microscopic scale to be able to grab, quote unquote, this Majorana, place it with a field, and move it around and do some manipulation with this. But that's a basis for one of the ideas behind the topological quantum computing. The idea is that these Majorana states have zero energy, which is guaranteed by this argument, and therefore they're decoupled from the rest of the system, and because they're chiral, they don't backscatter, so they're also immune to disorder. And so if you could somehow realize qubits based on the Majoranas, which by itself is non-trivial, even in the thought process, then the idea is that maybe somehow this could one day lead to quantum computation. And there are attempts to actually try to do this, for instance, at Microsoft Station Q. They're not actually using people's AP superconductors. There are a different set of ideas. But the main idea is that you create Majoranas and then you somehow manipulate them. Okay? All right, so I only have about 12 minutes left before the end of the lecture. Yes, question?
About that graph, he was just thinking about the point that the right and the left line are meeting each other. It has energy zero. Is that acceptable?
Right, so what I meant is that, so you should think of this being a left mover and this being a right mover. They have opposite velocities, opposite group velocities. So this particle moved to the right, but as they move, they might also have zero energy, right? Because remember, the velocity is just the derivative of the energy with respect to, in this case, n, right? So there is nothing wrong with particle passing through zero. What this means in practice is that the Majoranas would be an in-gap state that would be trapped right at zero energy. So that line right in the middle of my graph is where these two Majoranas are going to live, right at zero energy. It's very similar to what Jean-Noël told you towards the end of the lecture, that if you create, let's say, a Haldane state, and then you look at the boundary between a Haldane non-trivial phase and a vacuum, there would be an edge state whose energy would actually be exactly at zero energy, even though the bulk material has a gap. It doesn't have any states at zero energy. It has a finite gap, in this case protected by superconductor. Yes?
Sorry, so I'm a bit confused though, because for anyonic statistics, so my understanding is that for anyonic statistics to be defined, your anyons need to be sort of like localized in Bayesian massive, right, in order to like define this sort of like braiding system. Is that not the case here?
No. So the general idea of the non-abelian anyons and braiding is that you need to have a multiply degenerate ground state. In other words, the ground state is not just one well-defined wave function. It's like a spinor that has two components, 2 degrees of freedom. These 2 degrees of freedom in my example are provided by the fact that there are two Majorana modes, one coming from the left having zero energy, should use this graph, and the other coming from the right having zero energy. So over here there is like a superposition of the green particle, whatever is it, yellow, and the white one, and they both have zero energy, which means my ground state is now doubly degenerate. And think of degenerate perturbation theory. If I have a degenerate ground state, I could try to do some manipulations. I could think of the phases between psi1 and psi2 as being a phase living on a Bloch sphere, and now I could form linear superpositions. So that's the idea. The qubit would be superposition of, let's say, 1 and 2, where 1 and 2 is not up and down, but it's actually one Majorana or the other Majorana. That's really the basis of it. right? The only other thing I would say is that in practice, if the Majorana in any finite system, they might hybridize with each other. So strictly speaking, they're not exactly at zero energy, they may be anti-repulsion. Again, remember degenerate perturbation theory. If you take like Stark effect in a hydrogen atom, if you take two exactly degenerate ground states and you add a small perturbation, as long as it's allowed, you will generally lift that degeneracy, right? You will split the state. So the proper way of saying it is that in thermodynamic limit, meaning when the system size becomes infinite, when the boundaries are far, far away, the Majoranas don't talk to each other. It's easiest to demonstrate here. When the size of my annulus, the ring inside, is big, the blue mode does not talk to the yellow one. If you make this annulus very, very small, of the order of the coherence length, right, which is determined by like 1 over delta, that's when you get in trouble. Okay. Now, given the short time that is left, let me see where we've got ourselves. So we've covered these three things, right? And now the turn is to come to talk about three-dimensional superconductors. Let me just wave my hands a little bit and tell you that there is an interesting way how you could define a topological invariant in 3 dimensions, which at first seems not at all obvious how you would do this. Because in 3 dimensions, let me erase all of this algebra and fall back onto pictures and geometry. So remember I told you that the reason why Chern number could be defined in the first place in 2 dimensions was because in 2D you could think of the map N as the map from S2 into S2, and therefore we were looking at this object, which is a group of integers, and that's exactly where our Chern numbers live. Now, if you imagine doing it in 3 dimensions, you would find that there is a problem. I could still define a vector n in the sense I've defined that depends on real and imaginary part of the gap. But there's seemingly a problem because now, if I start from a 3-dimensional space, I could compactify it using stereographic projection onto so-called 3-sphere. Now, 3-sphere is something that's hard to visualize. It's a surface of a 4-ball. So a ball that lives in a 4-dimensional space, and its surface would be a 3-sphere. So it's a bit hard to think about this, but it's something where instead of just 2 angles, theta and phi, there is a third one in the third direction. Okay. So then the map would be from S3 to S2 because my target space is still a unit sphere. So what I'm going to do is this. It turns out that there is a very non-trivial map. So it turns out that this homotopy is actually also non-trivial. Remember, the 3 standing over here is a reflection of the base manifold. And it was first discussed in mathematical constant by Heinz Hopf, who was a German mathematician, and we are talking roughly about 1930s. Okay? And it turns out that the work of Hopf actually mimicked that of Paul Dirac and his discussion of the Dirac, what we now refer to as the Dirac monopole. It turns out that the two of them are actually closely connected. In my notes, which will be available online, there is more discussion of the so-called Hopf Fibration, and it's a clever fiber bundle where locally what you do is that you write down S2 on S1, meaning that, and so this is your fiber bundle. I think, I forgot what John Nael called his base space, but if this is V and this is F, a fiber, basically on each point in a 2-dimensional target space, there is a bundle associated with another circle. So it's a circle living on top of a sphere. It's a hard construction to imagine, but that's how the map is established from S2 back onto S3. And that's the so-called Hopf bundle. So in short, it turns out that you could define the equivalent of a topological invariant. You wouldn't call it a Chern number anymore. And there is a formal expression for what that would be. I'll call it N instead of C. And essentially, I'll just give you a final formula without deriving it, and the details are going to be in the notes. That one way to write this down is this number is given by 1 divided over 32 pi. Don't ask me why this number. You integrate over 3-dimensional space, not 2-dimensional space. And what you actually do is something tricky. You insert here a Levi-Civita tensor, and you multiply this by a mu multiplied by what I called f lambda, mu lambda. Now contrast this with the Chor number, which was written like this. Chor number was 1 over 2 pi integral over 2 dimensions. Let's say this was a number 3. And then therefore what was standing here is epsilon mu nu 3 multiplied by f mu nu, right? So the Chor number, this is the question about the indices, right? You insert the Levi-Civita tensor over here, and you essentially integrate Berry curvature. Here you take Berry curvature multiplied by the Berry connection. That is an object that has 3 indices. You form a totally anti-symmetric combination out of it, and you integrate it over 3 dimensions. So this is a so-called volume form in differential geometry. I won't go through the details, but essentially this is a well-defined integer, and there is a mathematical theorem tells you that n can only take integer values. And the short of it is that the B phase of helium-3 is the only unambiguously known 3-dimensional superfluid that is topological that we have. And in this so-called B phase of helium-3, I won't go into details of how the other parameter looks like. It would require more time that we have, but basically it's given by this number. So this number over here classifies the B phase of helium-3. The Chor number discussed here classifies the P plus IP superconductor, of which I spent the bulk of this lecture discussing. Till recently, there have been suggestions that there is one material which seems to realize this P plus IP, is the so-called strontium ruthenate. Again, for experimentalists in the audience, you may know about this. So there was a suggestion that the strontium-2 ruthenium-04 was the best candidate material that we had for having P plus IP superconductivity. I say we had because now there are doubts whether it's even P wave, and at the moment the experimental situation is murky, right? So as far back as 5 years ago, people still claim this was P plus IP. Now the situation is less clear. So probably it's fair to say that at the moment the only known superconductor / superfluid that's actually topological unambiguously is the B phase of helium-3. The topological invariant is a bit nasty. It looks like this. So it's not immediately clear. It's not really a Chor number. It's something else, but it's closely connected to it. So I'll end the lecture by stating that it turns out that all of this stuff that I've discussed today was essentially an attempt to show you case by case and interesting examples of where topological superconductivity can come. Now you could try to be more ambitious and ask, okay, but is there some more general framework? Is there some general understanding when I can and when I cannot have topological superconductivity? And that was developed, as I mentioned in the very beginning, around the year 2008, 2009. The references are going to be in the lecture notes. But what became known is sometimes referred to as a periodic table of topological phases of matter, non-interacting topological phases of matter. And the way this works is that you look at the structure of the Hamiltonian at a very coarse-grained sense. You don't worry about whether it looks like a Pauli matrices or not. You just look to whether or not it has certain discrete symmetries, namely time reversal, which John Noel talked about, particle hole symmetry, which is what I've talked about in the case of superconductors, and the so-called chirality. And based on those 3, you could define, it turns out, 10 classes of matrices, right? Historically, this goes back to Wigner and Dyson, who tried to classify the Hamiltonians of the nuclei. The problem was what? That if you take some heavy nuclei, there are multiples neutrons and protons in it. We don't know the details of the nuclear strong forces that would require QCD. It's complicated to solve. So let's just assume that there is a Hamiltonian which we don't know. Can we say something about the spectrum? At first you say, well, I mean, it's crazy, right? If I don't know anything about Hamiltonian, what do you want me to do? it turns out that while you cannot predict exactly where the levels are going to be, for that you would need to know the Hamiltonian, you could make a general prediction about how far the levels are going to be spaced. You could make a histogram. In other words, you could ask, what is the probability of my two levels being within 1 microelectron volt within each other? And that's a sensible question to ask. Or on average, within a given energy window, how many levels are going to be 1, 20, or 1,000? That's structure of so-called random metric theory, and it's based basically on this very coarse-grained view of the Hamiltonians. So the short of it is that based on this work, we now know that in 3D, there are exactly three classes of possibly non-trivial topological superconductors. These classes go by strange names, which I'll explain in a second. One of them is D3, and this corresponds to the B phase of helium-3. The other of them is called A3, and there's a class called C1. Now, we need to thank the French mathematician Élie Cartan, who back in 1930s, don't ask me why he came up with these bizarre letters and numbers, but he defined classes of matrices when he was studying Riemann surfaces, right? It's a beautiful branch of mathematics of which I'm not an expert to tell you about. But basically, the bizarre nomenclature goes back to Élie Cartan. The funny thing is that we still have not a single example of a superconductor of these two classes. And so for those of you in the audience, be it theorist or experimentalist, the future is in your hands. If you're the first one to discover a superconductor, it's going to be in class A3 or C1. Okay, I can't speak about Nobel Prize, but the recognition will be yours for sure. Thanks. What would be the guidance? Well, I could tell you that, so if you think of class D3, the helium-3b has a very strong spin-orbit coupling, so spin is not a good quantum number. If you ask what's the difference between this one and this one, the A3 class has a well-defined U1 spin symmetry. So what does U1 mean? Means X and Y may not be well-defined, but there should be a good easy axis. So if you have an idea of some element that has easy axis, like easy axis magnet, if you could make it superconducting, that's a clue. This guy has to have SU2 symmetry, which is even easier task. That means forget about all the heavy elements, maybe cuprates, maybe you should focus on something that has relatively weak spin-orbit coupling. So spin is a good quantum number. The requirements, as usual, it has to be fully gapped in 3 dimensions. Cuprates are not, they have line of nodes. So the first task is to find a fully gapped superconductor. Second, probably the easiest, is to put this on the annulus geometry like this, thread a flux, and see whether or not you discover a Majorana quasi-particle that's spin at the vortex. That sort of would be your smoking gun. There are some other cases where you could measure thermal Hall effect, but I won't go into details, but there is also predictions that if you take a 3D bulk, you measure thermal Hall effect on the surface. When I say thermal Hall, remember, superconductor doesn't allow field to penetrate inside, so you cannot measure currents. Well, it's a superconductor. But what you could measure is a thermal current, meaning if you put gradient of temperatures, you could ask how fast does the heat flow from the left to the right side of the sample, right? Superconducting Cooper pairs do not carry heat, turns out, but the Majoranas do. And those can give you non-trivial contribution to the thermal Hall effect, which is another way of seeing whether or not you have topological superconductor. My time's up. I'll be around. I'll be taking my family on a short trip over the weekend, but I'll be here a bit today and then when I come back next week, in the beginning of next week. So if you have questions, feel free to ask me.